one more interesting definition. What about, let's say, 21 over here, right? Apparently, it's also internal nodes, so we should also consider that. In the case of an internal nodes consisting of two external child nodes, in that case, it will be considered as a binary search tree automatically, because if you look at it's a left subtree. This is the left subtree, right, over here, and this part over here is the right subtree over here, right? And every node, every internal nodes storing the key value should have its key value strictly less than 21. And for external node, we don't really store any key value, so you cannot find any violation witness which will violate that the key value is strictly less than 21. You just cannot find it. So that's why this external node is automatically satisfying the search property. Similarly, the right subtree over here is also consisting of just a single external node, which will also satisfy the search property. Let me write it down. It's actually quite important for you to know not only the complicated case, but also the simple cases. Let me write it down. How about orange? Okay, so for these two cases, right? External nodes satisfies the search property automatically. Because its left subtree or right subtree contains no nodes. And the consequence of that, let me use another color over here, and no nodes. And the consequence, if I may, let me put it here, the consequence of that is can't find a violation of the search property in either the left subtree or right subtree. Let's be a little bit more clear here. For example, let's say this. In this left subtree over here, does it really satisfy this particular definition? It does, because we say that every node in this particular left subtree must be such that the key of the node should be strictly less than, meaning that in order to have a violation, we should find a key that's strictly larger than or equal to the key of the root. Can we find such violation? The answer is we cannot, because there's simply no such violation. There's simply no node for us to even find some violation in the first place. So that's why it will be satisfied. It's really like mathematically, let me just write it down. For those of you who might be taking some logic course in math, for every x is a member of empty set implies any property of x is going to be satisfied. And this is a well-known axiom in logic, because there is no such x that will exist in the empty set. Empty set simply contains nothing, meaning that in order to argue that x will simply satisfy P, in order to disprove it, you must find such x that belongs to the empty set that actually make the P false. But the problem is you just cannot find any element in the empty set, meaning that this property can never be falsified, meaning that this predicate over here would just be holding always, right? Maybe I'm just repeating what your math professor actually was talking about in the math course, but it's also very applicable in our context over here to really know why. In the case of the external node over here, as a subtree, it simply will satisfy the search property automatically. That's very important for you to understand. Let's now move on with the slides. And the distinction between internal nodes versus external nodes. That's something I just mentioned on the iPad. But let's just go over the bullet point quickly just to recall. So we store key value pairs only in the internal nodes. For the external node, we simply, implementation-wise, we simply store some non-meaningful value, which you will see later. So recall we actually talked about header versus trailer in a doubly linked list or doubly linked node, right? And we are treating external nodes as sentinel nodes or guardian nodes in order to simplify the logic for our BST algorithm. That's something we'll see. It's not really for improving the performance. It's not going to make a difference. However, for the simplicity of your code, it will help. as you will see when we define the different algorithm later. And so this is like annotated version. You can definitely look at the slides. So the green ones are the internal nodes, and the red or the pink ones are the external nodes. It's rather straightforward to see that, right? This is the same example tree as we illustrated. Okay. Let's now talk about the sorting property for the binary search tree. Given that a binary tree satisfying the search property will be called a binary search tree, and now we want to say, given a binary search tree, what kind of important property can we derive from there, so that when we actually do any operation, we might just be able to leverage such a so-called sorting property. That's something we want to see, right? That's kind of the logic where we're coming from. Let's now talk about it. An in-order traversal of a binary search tree will result in a sequence of nodes whose keys are arranged in an ascending order, right? This is the property. It's so-called sorting property of the binary search tree. So there are several key phrases over here. Number one, we're talking about binary search tree. Any arbitrary binary tree, which may not necessarily satisfy the sorting, the search property, may not have this sorting property. Okay. So number one, it has to be a binary search tree. Number two, we're talking about in order traversal, not pre-order and not post-order. It got to be in order. Number three, the resulting sequence is going to be arranged in ascending. It has to be ascending. Not descending, not non-ascending, not non-descending. It got to be ascending. Okay. Unless necessary, we may just only show the keys in the binary search tree nodes. That's something I just mentioned earlier. Right. So let's say this particular tree, we can use that to really check the property, and then we can justify why the sorting property is the case. But once we do the example, it should be quite obvious to you why this property will be the case. Let's now just verify that quickly. It might be nice to do some exercise about tree traversal, which we covered in the previous lecture. Let's now move on to this example tree over here. And this diagram just like a reminder just about how the search property is defined for the binary search tree. And for this one over here, so we're talking about some in-order traversal on the binary search tree. Okay. Of course, before you do the in-order traversal, you got to make sure this tree over here is really a binary search tree. How can you check it? We have to apply for every internal nodes, like the three I check as examples. But for you, I would suggest the following. You should really try to check for every internal nodes in the tree. Every one of them, right? Let me circle them just to show you. For every internal nodes in this tree, you want to make sure it really satisfies the search property over here. You want to make sure it is satisfied. Okay, and then we're gonna talk about in-order traversal. Let's do the exercise right away. For now, pause the video, and then can you tell me the sequence that's going to be generated from doing an in-order traversal of this particular tree? Of course, whenever you encounter external nodes, you can just ignore them, because conceptually they wouldn't contribute to any search key value. All right, you can now pause the video and do the in-order exercise. Alrighty, assuming that you did it, let's now say we can compare your answer with mine. Let me write down the in-order traversal, and we're going to do a little bit similar annotation as we did before, just to confirm the property, the sorting property. Okay, let me write it down. It's going to be 8, 17, 21, 28, 29, 32, 44, and then 54, 65, 76, and then 80, 82, and then we got 88, 93, and also 97. Okay, you can definitely check very easily to see that this sequence over here is actually sorted, but we want to make sure it's really the in-order traversal, right? Let's see how we can check that. And similar to what we did before, this is the root, right? 44. Okay, you can see 44 is somewhere around the middle. It's not surprising because somehow this tree is so-called balanced, but we'll talk about the balance property in the next lecture, not in the current one. Okay, and you can see this part over here is the left subtree, right? This part over here, the left subtree. And apparently this will be the in-order traversal you got from the left subtree. This will be the in-order on the left subtree over here. And what about the right subtree? over here, this will be the right subtree. Okay, let me just, okay, that should be good. That's the right subtree. And that's exactly what we got. Oh, let me do better. I want to cover all the elements. And this one over here will be the in order of the right subtree. Okay, and of course you can subdivide. Let me just do one more. Okay, that's basically what we did earlier. You can also try to do, let's say 17 over here. Let's say that's a root. So that's exactly over here. And then we got the left subtree over here. And also we got the right subtree over here. And apparently you can see this part over here is the, maybe let me use a highlighter. You can see this part over here, right? Is the in order for this left subtree. And this part over here is the in order of this right subtree over here, right? You can definitely try to do this exercise like an annotation recursively, like how we did it before. I'll let you confirm that. And this basically illustrates about why doing an in order traversal of the binary search tree is going to give you a sorted sequence, because whenever we do it recursively for every internal nodes that we have, because we know it actually satisfies the search property, is guaranteed. When we do the in order traversal, by definition we have to visit all the nodes in the left subtree first, in which case we are revisiting all the nodes with strictly less value for the key. And then we do the parents, and then we try to visit all the child nodes with the key values strictly larger than the root. And this will be done recursively. So that's why the generated sequence will be exactly sorted. All right, let me summarize what I just said and illustrate it in the slides. Justification. Number one, in order traversal by definition is going to go for left subtree for all the nodes, and then go for the root and go for right subtree. Right? So if I go for in order traversal for left subtree, it's guaranteed. After in order traversal for this left subtree over here, I'm going to get a sorted sequence for this left subtree. And every element there is going to be strictly less than 44, given that the entire tree is binary search tree, satisfying the search property, and symmetrically for the right subtree as well. And the second part of the justification, because the search property is actually guaranteed to hold, otherwise we wouldn't call this a binary search tree. So that's why the property, the sorting property is so important. The precondition is the tree we are talking about must be a binary search tree, otherwise it wouldn't hold. And we know by definition for the binary search tree, all the elements in the left subtree has their key values strictly less than the root's key, and symmetrically every the keys for every node in the right subtree must be strictly larger than the root's key, right? So these are very important two aspects you want to think about. They very often work together. One is about in order traversal, and the other one is about search property for the binary search tree. All right, so that's about enough introduction to the binary search tree. We talk about its recursive definition, we talk about the search property, and we talk about the sorting property given a binary search tree. Let's now move on to talk about how we can implement a binary search tree.